Hello, welcome to Econometrics Melody. In this tutorial, we'll deal with different kind of matrix function in Stata. With this main Stata interface active each time, press Ctrl 8 for activating data editor and Ctrl 9 for activating to file. Let's begin. Let us clear everything. This results in a scalar matrix or a scalar value because we have only one value enclosed within this big bracket, and the matrix accepts both big bracket or a small bracket. And let us create a row vector. So this is a column join operator, comma is a column join operator, and it creates a new column. And backslash is a row join operator, it creates a new row. So this matrix B is a row vector. Matrix D is a 2 into 3 matrix. So if you see, we can use both small bracket and big bracket. So in order to create matrix or manipulate matrix in Stata, we need to write matrix, though there are other programs, meta and programming language also does have certain matrix manipulation. Now let us create a matrix E. This is a 3 into 3 matrix. And if you want to change or manipulate any special element of certain row and column of this order, then you can also manipulate by referencing the name and the position of the matrix. We are going to change the first row and second column element of E by 99, and let us see the result. So previously first row and second column of E, previously it was 11, now after this change it is 99. Similarly, we can extract the matrix submatrix from a matrix. We are going to create a matrix J from matrix E by taking 1 to 3rd row and 2nd to 3rd column. So this is it. So 1 to 3rd row and 2nd to 3rd column. So this is a submatrix. Similarly, another matrix K is also a submatrix after taking 2 to 3 3rd row, 2nd to 3rd row, and 1st to 3rd column of matrix K, matrix E. Now as E is a square matrix, so the sum of the main diagonal element, it is called as trace, and we are going to manipulate this, and 69 is the trace. We have added this, and we have inbuilt function called trace to calculate the value of trace, and let us see whether they are same or different. Yeah, it's same. Now let us try some addition, subtraction and multiplication of the matrix. We are going to create two matrices E and F of different order. E is a square matrix, F is a 3 into 2 matrix. We can see this, there are elements. Now call names, so we can change the name of the columns. We are going to change the name of the columns of matrix F. We have two columns and we want to name it OK and seat. Similarly, we want to change the name of row. So there are 3 rows, we are naming it we, us and me. So this is the function row names. Now for multiplication, we assume that we know the matrix multiplication property. So the column of the first matrix must be equal to the row of the second. The number of columns of the first matrix must be equal to the number of rows of the second matrix. So the resulting matrix will have the rows number from first matrix and column numbers from the second matrix. This is an example of addition of matrix. This is an example of subtraction of the matrix. And this function rows of I will display the number of rows of matrix I. Calls of I function displays the columns of number of columns of matrix I. Now let us generate some data E, F, G and regress them quietly. The results are hidden. So E return, whenever there is estimation like X, for example, regression, so E return will display all the values that are stored in E class. So these are the E class, and we can call them by matrix notation. So we can reference or we can call them. We'll see an example. R return, or simply it's a return stores the results, and these are the results, scalar and matrix results. So we'll make use of this. In our earlier videos we have also referenced E return and return. Now let us go to the function I. So capital I, it results in the identity matrix of order as is specified here. So if you want to say this is a 3 into 3 identity matrix, and if you want the upper triangular value also to be displayed, then you can use this no half. This is our 3 into 3 matrix E. We want to find its inverse, and we multiply the matrix by its inverse and check whether it's identity matrix or not. And if you want to display the upper half of the matrix as well, then this is the result. So it's minus 15. This indicates that 3.553 should be divided by 1 followed by 15 zeros. This is also nearly equal to 0. It is 0 actually. Now we use this function invsym. This function is used to calculate the inverse of the symmetric matrix. Though our matrix E is a square matrix, but it's not symmetric. So in order to make it symmetric, in order to derive some symmetric matrix, we use E transpose E. Now this is the symmetric matrix. Let us find its inverse and let us list it, and let us check. We have formed the inverse, we multiplied the matrix with its inverse, and we're checking whether it's identity matrix or not. Again, this value divided by 1 followed by 14 zeros, this is almost 0. Very close to 0. Now let's try the Cholesky decomposition. Matrix L, it's a symmetric matrix, and Cholesky decomposition works for symmetric matrix. So a matrix, when this product, they result in a symmetric matrix. Now let us see whether it's a symmetric matrix or not. So it's a symmetric matrix. Now let us derive M as a Cholesky decomposition of matrix L. So let us list this. So M is a Cholesky decomposition of matrix L. So when this is divided by its transpose, we get the original matrix, and we're going to check whether this is true or not. So this is N, and this is no different than L. They are equal. So let us say this, it's exactly 0. Let us try the next function, matrix function. It's correlation. It derives the correlation of any variance matrix. If we assume V to be the variance, so V is a variance matrix from the regression that we had run earlier. So this is the variance. Now if we want to calculate the correlation, this is the variance of beta. So what is the correlation of beta? Let us use this. So this displays the correlation matrix, and if you want the full thing to be displayed, the upper half also to be displayed, then we write no half. Let us see. Now if you want to create the diagonal matrix of any row or column vector, we use this command. Now we have a row vector, 1 2 3 as the elements. Now if we run this, then we have 1 2 3. The off diagonal elements are 0. So if you want to say, let's write no half, and you can again run this. You see, it's a column vector. Let's try the same thing with the column vector. It's a column vector, main diagonals. So this is the use of diag. So hadamard, this hadamard will needs the same order matrix, and it will apply the element by element multiplication. This is very simple. And if you want to test whether this statement is true or false, from H we are taking first the element 1 1, and from I also we are taking element 1 1, and let us run this, and we check the value of T, whether this is the first element. This is circle. Let us try once again. First row, second column element value, and the first row, second column value of matrix I, first row, second column value of matrix H, and if we multiply this, and we should get the T first row second element, T first row second element, minus this, we get minus this. Okay, so we can say that hadamard, it results in element by element multiplication of same order matrix. So this is to create a matrix with this value. So we are going to create a matrix 3 into 2 of order 3 into 2, and the value is minus 3. This is very simple. Matuniform is the R uniform version of matrix, it creates the uniform that ranges the value that ranges between 0 to 1. This is again very simple. Nullmat, so this is to specify during the programming to specify the matrix to be null. And sweep, we are going to sweep the row or column. Here we are, the example we are taking to sweep the second either row or column. And let us see the matrix and let us apply this formula, and if we list this we get this value, and our input was matrix E. Now how did we get matrix X? So we have taken second row or element, so second row and second element, this value is exactly the reciprocal of this. If we see, this is the second element, second row second column element, and its reciprocal is this, and the value X, second row second column, its value is this. So as we have taken 2, that is second, so we make use of this second row second element, second row second column. So this element at second row and second element, second row and second column extensively to calculate other elements of X. So this results in x11, this results in x33. We have calculated the main diagonal elements, x13, x31, x12, and you can check it, x32, and there is a very simple formula. Now let us, this function vecm, it stacks the column of vector E and forms a column vector. You see, matrix E, this is the matrix E, these are the columns 34, 19, 24, 11, 16, 11, 16, 13, and so on. Vecdiag, so this function, it extracts the main diagonal elements and it results in the row vector. See, the main diagonal elements are 13, 16, and 19 of matrix E, and we have extracted due to this function called vecdiag. This is very simple. Now let us jump into other functions, other matrix functions that results in scalar values. So matrix F, this is the matrix F, and we are going to ask which column of matrix F has this name. So this is the column number, which column, okay, column number. So it is very obvious by the function name itself. In matrix E, we want to find the number of columns of E. There are 3 columns, determinant of E, and diagonal, does the diagonal element contain 0 or not. So matrix E does not have any 0 in the diagonal element, so it is false, so that's why we get 0. And this results in, so I have specified in the in the matrix V, so this is the row, this is the column. So if the rows or columns are specified in decimal numbers, then it takes the floor value and results the respective element. So V32, what is our V32? Let us see our V32. Did we display it? So let us display it first and then we see. So V32, okay, what is V32? This is V, and third row second column, so this is the result. So is symmetric, this is very simple. Whether the matrix E is symmetric or not, no, so we get false, 0, because matrix E is not symmetric. Matrix L, yes, matrix L is formed after, so matrix L is formed due to this. So let us check matrix E. Yes, it is a symmetric matrix. Now matmissing, whether the matrix, any element of the matrix is missing or not, no, matrix E does not have any elements missing. So real difference between two matrices H and I, this has some formula that I'm not displaying right now. This works. And matrix, let us work on matrix F, a row number. So in matrix F, which row does have the name V? So is it first, I guess? Yeah, it's the first row. You see, first row we have V. Now rows of E, how many rows does the matrix E have? It's 3 rows. Similarly, we have already tried this trace function, it was 69. in other of the cases. Now let us see some of the useful functions. The singular value decomposition of matrix E. Again, matrix E is not it is a square matrix, but it's not symmetric. So let us calculate its singular value decomposition, and we have three results: U, V, U, W, and V. So let us list them. What are the U, W, and V? So this is the U, W, and V. So U transpose U, this will result in identity matrix. V transpose V also will result in identity matrix. And to get the matrix E, we use this formula: U diagonal of W and V transpose. Let us see, and let's check whether the matrix is equal to E or not. So matrix B, we have derived it by using this formula, and E, they are one and the same. Now let's check its property. So U transpose U, they are identity matrix. So the main diagonals are 1 and the off diagonals are 0. You see, this divided by 1 followed by 16 zeros, same is the case, and here 17 zeros, minus 5.51 divided by 1, 17 zeros. So they are 0. The off diagonal elements are very close to 0. I mean, they are really 0. Okay, now let us use another function, symeigen. So to calculate the eigenvalues of a symmetric matrix, L is our symmetric matrix. We have this main diagonals, and this is like the image of. Okay, so now let's calculate the eigenvalues of this symmetric matrix, and here X and V is the eigenvalues. So we get X and V is the result. Let us say this. So this is X and this is V, eigenvalues. X transpose X is also equal to identity in this case as well. So we have, let us now multiply the original matrix with this X. Whatever result we get, that is equal to XV, that is equal to X diagonal V. And if you list them, they are one and same. Similarly, X transpose X is an identity matrix. Again, you have 16. The off diagonal main diagonal elements are 1, and the off diagonal elements are 0. They are 0. Don't confuse with this value. So this is 1.110 divided by 1 and followed by 16 zeros. So they are 0. Now let us use a very interesting example. So this decomposition is used to calculate the nth power of any matrix. Let us say this, any symmetric matrix or any matrix as well, if you know the eigenvalues and this vectors, the list of eigenvectors. So as we know Lx equals to xv. Therefore our main matrix L is equals to X diagonal V into X transpose or X inverse. So as X transpose X is equals to identity matrix, the transpose of X actually is equal to its inverse. So we have L equals to X diagonal of V into X transpose. So let us find the cube of, as an example, this is very interesting. Let us find the cube of matrix L. So this is very simple. We multiply L 3 times, we get the cube of it. Now another way, once we have decomposed or once we have found its eigenvalues and vectors, you see, we take the diagonal eigenvalues and we multiply it 3 times. So we could have taken the cube of eigenvalues and multiplied it with the original X and X transpose. So this is very simple way of calculating. Let us check whether they are same or different. This is the usual way, and this is by cubing the diagonals. You see, they are the same. Let's say if you want to calculate L to the power 100, then you simply write V to the power 100 and you multiply with X and its X transpose. This is very interesting result, decomposition. Now let us calculate the eigenvalues of the matrix. So this matrix E, we are going to, it is a square matrix but not symmetric matrix. E is a square matrix but it's not a symmetric matrix. We are going to calculate its eigenvalues, and the eigenvalues has two components, the real and imaginary component. So what is its real component and imaginary component? Is the imaginary component is 0, so this is the eigenvalue itself, and they are ordered from highest to lowest. If we had some complex values as well, if it was non-zero complex value, then this is the formula to calculate the real eigenvalue. It's the square of sum of the square of real component and imaginary component. It's a square root, so they are the same. Now let us use this matrix to derive the OLS beta, its standard error and t values. So let us generate these values. We have y, x1, x2, x3 and I for constant. The usual way of deriving beta is by regressing the values. Here y is dependent value and rest are independent values, and e return list, actually this is an estimation regression. We have used the regression command. Now we have some estimated values stored within this e as a suffix, a function e, let us call function e or e class. So return list, this gives the result. These are the results. So we'll make use of this in our later part. Now let us try using the matrix. So we have variable y, so we convert the variable y into matrix form. So this I is for constant, and we have other variables, independent variables x1, x2, x3. So let us also convert it into its matrix counterpart, and we store all these values into matrix X. So to calculate the value of beta, it's x transpose x inverse x transpose y. We know this famous derivation, and let us check. So we have run a regression in our earlier case. The value of beta is stored in this function eb. So this is the value of beta, and let us check this with the value of beta that we have derived. So are they same or different? Yes. We have x1 minus zeta, okay, x2, x3, and this is the constant I for constant. Okay, now let us derive the variance. In order to derive the variance, we need to calculate the residual, its sum of its square, and divide it by degrees of freedom. And the variance of beta is sigma e square and x transpose x inverse. So this is the value of. Now let us check. This is using the regression, directly referring from the regression result, and this is the result that we have calculated using matrix. And if you compare them, this I is for constant, here this is the result from Stata, and if you compare this, they are exactly the same. Now let us calculate the t-test or t-statistics. So let us regress this once again, so that the result on our table is not lost or written again. So this is the result, b standard error t. We are going to derive this. So this result is due to this regression or Stata inbuilt functions or codes of result, okay, due to the Stata inbuilt results after running regression. Now let us try to calculate this using our matrix. So we have matrix EB from Stata, okay, and matrix EB from Stata. We do have this matrix EB, variance of beta. Now in order to calculate the standard error, we take the main diagonals from this main diagonal elements, and we make a column vector, and we use this because we need to divide. The element by element division is not possible using this function, so we take the reciprocal of these elements and take the square root. Now let us see what is the value of standard error. This is the standard error, and this is the standard reciprocal of the standard error, and we'll make use of this. Now let us find the value of t. T is equals to hadamard. This is this results in element to element multiplication. So we have this beta stored in this vector, and we have this reciprocal of the standard error. So if we multiply this, it is equivalent to dividing a beta element by this standard error. And let us see what do we get. So this is the value of t. So t14, this is the value of t. And if we compare this with matrix table, we see this is the value of t, this is the value of t. Now if you want to really order it in a nice format, and again, so we have ordered this beta, we have derived it using matrix, se we have derived it using matrix, t we have derived it using matrix notation or matrix form. Now let us rename this. We have the first one is beta, the second one is standard error, and third one is t. Now let us compare this result with the matrix result. You see, so this beta, yes, standard error, and t we have derived it using matrix, and this is the Stata inbuilt result after regression. So let us compare beta. They are equal, standard error is also equal, and the value of t, they are also equal, 0.7928, that's equal. If you want to explore more about the matrices, you can refer to this books. Actually, these are the guides from Stata, programming, user guides, D for data management, and M for mata. Please take your time in understanding these concepts. They are very useful, and we do have other variations or other way of calculating mathematics dealing with matrices. So thank you very much for your time. Thank you very much, Econometrics Melody.